In this video, we're going to look at aligning surfaces together. By alignment, we mean achieving a certain level of continuity, whether that is G0, which is position, G1, which is tangency, G2, which is curvature, or G3, which is slope of curvature. Most of the heavy lifting is done by the align function, which we find under Object Edit. In this case, if we wanted position continuity between these two surfaces, we would set G0 in the menu, and because we're trying to align edge to edge, we set the alignment type as edge. Now you can see that we've got position continuity here, and you can tell that because we've got a green P symbol. If we go to G1 continuity, we're now affecting two holes, the first and the second, and we've got a green T symbol, which denotes that we've got tangency continuity between the two surfaces. Taking it to the next level, G2, this is curvature, so we've got a green C symbol, and we're affecting the first three holes now. If we go one step further to G3, that's now affecting four holes, but you'll notice that the symbol doesn't change. There is no special symbol for G3. The Align tool does most of the work for us, but there are times when we need to manually move CVs in order to achieve the continuity that we want with the surface quality that we need. Before we look at alignment, we need to understand exactly what we're measuring when we're analysing the continuity. Here we have two surfaces where there's clearly a gap between them. Now if we go into Evaluate SurfCon, and have a look at G0 positional continuity, it's telling us that we've got position continuity between them, which clearly we haven't. So what's going on here? If we go into the information window, we can see that we've only got one checkpoint. And what that means is that we're getting one checkpoint in the center, and then two at each end, so three in total. And clearly at the center, where these are crossing over, these are positionally matched, but of course where we've got this large gap, we're not getting any report of a problem at all. If we increase the number of checkpoints, then we're going to get closer to the maximum gap value. As we increase the checkpoints further, we'll get closer and closer to that value. When we used SurfCon originally to assess the G0 continuity on these edges, we only had one checkpoint. Now where did the number 1 come from? In fact, it comes from the construction options. So this is the value curve fit checkpoints, and it's currently set to 1. We can use the slider and make it 10, but we can actually type in 100, which is the maximum number we can go for, which is what I would recommend. So now when we go into SurfCon and we check position, we get a more sensible number of checkpoints. The other value that's very important when we're looking at position continuity is the maximum gap value. And if we look in the CATIA V5 preset, we can see that it's set there to 0.001. What this means is that if we were to read our model into CATIA and all our gaps are less than that tolerance, then CATIA will treat those surfaces as being watertight, in other words, without any gaps. So we should set our value to 0.001 or less for CATIA. I would recommend setting it to something like 0.0009, just in case we're missing the maximum gap even though we've got 100 checkpoints on our edges. If you want to know the exact values of the gaps at each of the checkpoints, you can go into Windows, Information, Deviation Table. And here we can see a column of all the gap values, including the maximum and the minimum. Let's change the number of checkpoints back to 100. Now so far we've been looking at a particular type of spacing, which is per span, but we can also set the spacing to be arc length, in other words based on the physical distance along these edges. So here we've got a check distance of 1 millimeter. If we look at the maximum gap, it says 19.668. If we change that back to per span, we've got 19.6678, so slightly different gap. So depending on which of these we choose, we get a different result. The disadvantage of arc length is that for very small edges we might not have enough points, and for very long edges we might have far too many points. Another example of where we get different spacing of checkpoints is when we're looking at natural edges versus trimmed edges. So if we look in the information window, we can see that they're both per span with 3 checkpoints, but we're getting a different result on the trimmed edge to the natural edge. The reason is that a trimmed edge is created from a curve on surface, and a curve on surface is a multi-span degree 1 curve. And so because it's multi-span, we're getting more checkpoints than we would on a natural edge. Next we're going to look at G1 or tangency continuity. Again, we're going to go into the construction options, and under continuity we have normal angle G1. So this is the tolerance that we're setting for tangency continuity. So if we're using SurfCon, for example, and we come up with a green T, that means that the angle between those two surfaces is less than the value that we've set in this menu. I would suggest that 0.05 is a good value. That's 3 minutes. But of course, you should always consult your company standards to see what value they require. Next we come on to curvature or G2 continuity. So if we look in the construction options menu, we have a value for this, 0.1. And where we've got a green C symbol, that means that's within that tolerance. But what does that number actually mean? Perhaps the easiest way to understand what the value of G2 means is to look at curves rather than surfaces. It's the same principle whether we're looking at curves or surfaces. So here we've got some curves, some of which are aligned in G2 and some of which aren't. So if we go into evaluate CurveCon, we can specify curvature, and then by picking on the ends of these curves we get the values of G2. So you can see that this one has a value of 0, where we've got G2 continuity. At the other extreme we've got this one where on the right hand side the curve has gone completely flat, and we've got a G2 value of 1. And then as the curvature increases on the right hand side, we're getting progressively smaller values of G2. So if you remember, in our construction options we've set 0.1. So in other words, this condition here is just inside tolerance. These conditions are outside of tolerance. So if you want to know the mathematical formula behind G2 continuity, it's this. So it's the difference between the end radii divided by the sum of the end radii. Now notice that this formula uses the radius values, not the curvature values. For example, if we have two curves where the end radiuses are the same, then the difference between them will be 0, and so G2 will be 0. If the end of one of the curves is almost flat, then the radius value will be very large. So the difference between the end radii will also be very large, and the sum of the end radii will be almost the same value, and so G2 will tend towards the value 1. Analysing the G2 continuity between edges is obviously very useful, but there are times when we may not be able to achieve 100% curvature alignment. For example, this edge. In this case we should rely more on curvatures and highlights to assess the quality of the surfaces. When we've got a group of surfaces like this, rather than checking each individual edge, we can use Checkmod. What this allows us to do is to check multiple surfaces at once. So we're checking surfaces, we're checking all of the visible objects, and we're just going to report on the errors. So for now we're just going to look at distance, which is down here, G0, and you notice it's got a tolerance of 0.0009, and that's come from the construction settings. You'll see that some of these values are greyed out, so we can't actually edit those anyway. Some of them aren't greyed out, so we could change those. But the values that we're interested in at the minute are the gap tolerance, that value there, and the topology distance. I'm going to explain the topology distance in a bit more detail in a minute, but it's a way of checking whether an edge is a free edge, such as this one, so there's no other edge adjacent to it, or whether it's next to another surface. So this edge, for example, here, as long as it's within that topology distance, 0.5, then the analysis will take place. So now we press check, and it will come up with any errors. So you can see there's one edge there where there is a gap, and the surfaces that are affected by that are in this table down here. So if we go into the information window and have a look at that locator, it tells us that it's checking the spacing by arc length and that the distance is 100 millimeters. The question is, what is deciding that that's arc length rather than per span? Well, the answer is that if we delete those locators, get rid of this menu, it's whatever we set in SurfCon when we last used it. So you can see in SurfCon we've got arc length 100 here, but as I've said before, per span is probably the best option, so we should always have this at per span. So if I press go and pick some edges there, so this is now using a per span of 100. If we get rid of that, go back into Checkmod and run the check again, and then we look at the information window on that locator, you can see it's now changed to per span and 100 checkpoints. So that setting and that value are coming from the last use of SurfCon. Now I mentioned topology distance before, which is set to 0.5, and this is another value that comes from the construction settings. So you can see down here it says 0.5 in this menu, and that's where that value comes from. These values that are greyed out here can be edited if we use custom tolerances, but I wouldn't recommend that we do that in general. It's better to be consistent with all our values. Let's have a look at topology in more detail. So here's an example where we've got two surfaces with a varying gap in between them. So in the first three cases, the intention is that there is G0 continuity between these edges. In the last case, we've got a deliberate gap. So let's analyze those edges. So first of all, we're going to use SurfCon, and we're looking at position continuity and per span as usual. And here you can see that's within tolerance, so in other words within 0.0009, which is what we've set in our construction settings. This one here you can see there's a bit of a gap error of 0.05. This one's also got an error which is bigger, it's 0.6. And the final one, which is a deliberate gap, is 1 mil. So we're happy that that is as it should be, but these ones aren't necessarily correct. If we delete those locators, and we'll run the analysis again, but this time we'll use Checkmod. So in Checkmod we've got G0 0.0009, and we've got our topology distance of 0.5. So when we press check, let's see what happens. So what we're seeing there is no gap here, which is correct. It's within 0.0009. It's telling us there's a gap here, which we know there is, so that's okay. But this one, it's missed out completely. This one, we're not expecting to see any analysis because we know there's a deliberate gap there. So what's happening in this case? So let's go back to our Checkmod menu. The problem is to do with our topology distance 0.5. So when this function looks at a set of surfaces, it's first assessing whether adjacent edges are within this topology distance. It's like a rough check on adjacency. And we know that these edges here are 0.6 of a mil, so they're slightly outside of that. That means it thinks that these edges here are free edges, much like that's a free edge. And these ones are free edges, which we know they are, because we've put a deliberate gap in there. But this one we want an analysis on. So what we need to do is increase this topology distance to a value that's greater than this gap. And we'd normally do that in the construction settings, but here, because it's quicker, we can just go into custom tolerances and we'll change that distance. If we were to set it too high, say 2 mil, then we're not only going to get an analysis on this edge, but also on this edge, which we don't want. So we need to set it to some value between the 1 mil we know exists here and the 0.6. So let's set it to 0.7, and we'll run the check again, and now we get an analysis on that edge as well. So topology distance is really a way of telling the system which edges do we want to analyze and which ones do we want to ignore. Another way to assess whether a group of surfaces are all within the position tolerance is to use stitch. So with stitch we just pick all of the surfaces and then press the space bar, and this will tell us how many groups of surfaces it recognizes. So if we look up in the user prompt area, it says it's created 2 shells with 4 boundaries. So if you look at the yellow edges here, that's showing 3 edges, so it's thinking that that's one separate part there, and then we've got another part here which has got 3 edges or yellow lines all the way around it, and then there's also a split in the middle, so another yellow edge there which shows that there's a gap bigger than the 0.0009 that we want. Now let's look at tangency or G1 continuity. So here we've got 3 surfaces which we want to be aligned in terms of tangency, and a 4th surface which is coming off at a distinct angle. So if we go into SurfCon and we put G1 tangent continuity on, we can go and measure those angles. So the first one is within tolerance, and by that I mean it's within the construction tolerance that we've set here, which is 0.05 degrees. The second one is outside of tolerance, it says it's 2 degrees. And the third one, which we're not really interested in, is 60 degrees. So that's a distinct tangent break that we want to maintain. So this one would be one where we'd need to align those. This one is already aligned. Now if we delete those locators and we go into Checkmod, so far we've looked at G0. We're going to take the custom tolerances off and set tangent angle G1 as 0.05. Again, it's grayed out because we can't edit it unless we use custom tolerances. So let's run a check on there, and you can see that it's picking up on this angle mismatch here. This one has passed the test, this one is being ignored. So how does it decide which edges to ignore, which edges to look at, and which edges are within tolerance? We go back into the Checkmod menu. We've set the angle tolerance at 0.05. That was set in the construction settings. So anything below that angle will be ignored completely, which is that edge there. This one is picked up as an error, and the reason it's picked up as an error is because we've got a tangent angle maximum value in here. So at the moment it's 4. That means anything between that angle and that angle will be assumed to be an error. Anything above 4 degrees will be ignored. So this edge is being ignored because it's 60 degrees. This one is being analysed because it's between that angle and that angle. If we were to change that down to 2 degrees, and we'll get rid of the current locators and run the check again, you can see it's not picking up on the whole of that edge. If we make that even smaller, let's make it 1 degrees. We'll delete those locators and run the check again. Now it's not picking up on that edge. So it's very important that we get this angle right. If we make it too small, it's going to miss some of the angles where there's a problem. If we make it too large, for example, if I made that 90 degrees, it'll pick up on edges that we're not really interested in, like this one. So usually I set this to about 4 degrees, and I find for most work that's absolutely fine. Lastly, with Checkmod, we're going to look at G2 continuity. Now first of all, we need to make sure that everything's tangent aligned in this area. So this one we know is tangent aligned already. This one needs to be aligned. So in the Align menu, we're going to put on G1, and we're going to align those surfaces together in terms of tangency. Now let's go into the Checkmod function, and what we're interested in this time is curvature. So we'll tick that on, press check, and we can see where the system thinks we have some errors. So this edge has passed the test, so this is curvature aligned. This edge hasn't passed, so the maximum curvature here is greater than our minimum value that we want, 0.1. This edge we're getting curvature analysis on, but we're not really interested there. We know that there's a tangent break, there's not going to be curvature continuity. Now the reason it's picking up on that edge is that our curvature maximum value here is set at 1. And if you remember, when it's set at 1 it means any curvature mismatch will be within tolerance. So we need to set that a bit lower. Let's set it to 0.5 for example. We'll delete all of those locators and run the check again. And now it's just picking up on that one edge, which is the only one that we're really interested in terms of curvature. Let's just summarize where we are so far. So if we go into Preferences, Construction Options, we've got Curve Fit Checkpoint at 100, Maximum Gap 0.0009, Angle 0.05, Curvature 0.1. And our topology distance we've set to 0.5. There are times when we might need to change that value. If we're dealing with very large geometry, then that would be fine. If we're dealing with very small geometry, then we may need to make that topology distance even smaller than that. If we go into SurfCon, I would recommend always setting that to per span. If we're in the Checkmod menu, the tolerances here, the ones that are greyed out, are coming from the Construction Settings menu. The tangent angle maximum we need to set at something like 4 degrees. In other words, any angles above that will be ignored, where we might have a deliberate tangent break. And likewise with curvature, if we set it to 0.5, then we won't pick up unnecessary curvature mismatches. Now that we've looked at measuring continuity between surfaces, we're ready to start to align them. So we take a very simple example of two surfaces here where we're trying to align one into the other in terms of position. So in the align function we need G0, and because it's edge to edge we'll choose the edge option. I've got explicit control off, so we're just trying to align those two surfaces together, and there we see we've got an alignment. Unfortunately, because we haven't got explicit control on, the degree and the number of spans is very high. It's degree 5 and 16 spans, and this is totally unacceptable for A-class work. So if we put explicit control on, and we've got degree 3, so the original degree, so you can see we haven't got an alignment between those two surfaces now. We've got a gap of something like 7.4 millimeters. Now the degree of this surface is degree 5 going this way. We might expect that if we increase the degree of this surface to 5, then we'll get an alignment. But unfortunately that's not the case. So the gap has come down, it's only 0.35 or so. But the reason we're getting a gap is because the CVs of this surface don't line up exactly with the CVs of this surface. So in order to do that, we can switch on position influence, and at the moment we've got position influence of 0, which means that the CVs on this surface stay more or less where they were originally. They're just going to be moved normal to this surface to try and reduce the gap. But if we increase the position influence value, you can see the gap starts to come down until we get to a value of 1, and we've now got 100% position alignment here. And you'll notice that the CVs are exactly the same as the CVs on this other surface. So this is a very similar scenario to the previous one, except this time this surface is a trimmed surface. So let's see if we can align those two. So the continuity we've got is G0, it's edge to edge. We want explicit control on and position influence of 1. And because we've got degree 5 in here, it's given us a perfect alignment. The CVs have been positioned exactly the same as the CVs on this surface. And so in this case, where we've got a natural edge of a trimmed surface, it's exactly the same behavior as if this was an untrimmed surface. So this is a slightly different scenario to the one before. We've still got a trimmed surface, but this time it's the trimmed edge that we're going to try and align to. So we want to align this surface to this one. So we have the same settings as before, G0, edge, explicit control, position influence of 1 with degree 5, and you can see we're not achieving an alignment. The gap is something like 0.02. And the reason is because of this trimmed edge. So we'll just take that back to where it was. A good solution in this case is to reapproximate this surface as a trim converted version. But we want to maintain the original trimmed surface as well for our final model. The trim converted version is purely for construction, and it will work well because this edge here, this trimmed edge, is very close to an isopalm. If it was an isopalm, then we could get 100% the same surface by doing a trim convert. Where it's slightly off that angle, then we can get a very good approximation. So let's go into Surface Edit, Trim Convert. So we want Keep Originals, because we want to keep the trimmed surface in the final model. And we're going to reapproximate that surface as a trim converted surface. Now what we've got to be careful of, because we want to use this for construction, then the natural edge of the trim converted surface should be very, very close to the trimmed edge of the trimmed surface. So we'll put edge deviations on and see what that gives us. We'll take the shading off so we can see it clearly. So it says the maximum distance between the trim converted and the trimmed version are 0.006, which really isn't tight enough. So we'll put auto update on and increase the degree until we get to 0.001 or less, and here it says maximum of 0.0. Now we can use this trim converted version to align this surface too. So if we go back into Align, we'll have the same settings as before, G0 edge, explicit control, position influence of 1. So we have to be careful which surface we're going to pick here. So at the moment we've got a gap, but if we increase the degree like we've done before to degree 5, we reduce that gap down to below the tolerance. Now we haven't had to increase the degree to match to the degree of this trim converted surface. Sometimes you will have to, but in this case we haven't had to do that. As I say, this is a construction surface, so we want to pick nothing and pick that surface and either delete it or put it into another layer. I'm just going to delete it. And now we need to check that we've got an alignment between our trimmed surface and the surface that we've now modified. So we're just interested in G0 continuity, and there we have a position continuity between the two surfaces. There's no guarantee that this would work with degree 5. It might well have been that we'd have to increase the degree to 6 or 7 in order to get that alignment, but in this case we've been lucky and we've managed to do this with degree 5. This technique of using a trimmed converted surface as a construction surface but keeping the trimmed surface is a really powerful technique that can help in lots of cases. So in this example we're just trying to align this surface in G0 to this surface. So first of all we're going to align. We're going to have G01, we're aligning to an edge, and we'll keep explicit control and position influence of 1 on. And you can see that the gap has come down. It's now about 0.3 of a mil. And the first thing that we do here is increase the degree and see if we can get an alignment. So I've taken it to degree 9 and it's given us G0, but because we've got position influence of 1 on, it's moved the CVs around. So our nice pattern of CVs no longer exists. So rather than having 1 on, we'll change that down to 0, so that gives us more of the original positions of the CVs, but we no longer have a G0 continuity. So let's try increasing the spans. So we can get it to degree 9, 5 spans, and we get a position alignment here. But the degree and the number of spans is far too high for A-class work. So let's undo that. So in this situation, what often works better is to use project. First of all, we need to untrim this surface, and we need to get rid of that curve on surface. So now we're going to use project in the menu, and what project does is it takes the edge that we've got and projects it onto this surface as a curve on surface. We need to make sure that the projection direction is correct, so we've got project with Z on, which is suitable for this case. And there we can see it's created a curve on surface and shown us the gap between the two, 0.1 of a mil. Again, we'll increase the degree until we get to the point where hopefully we get G0, which is there. So that's degree 7, one span, which is a much better result than we were getting from using the edge option. Now if we take history off here and we come out of the align function, what we have to be careful of here is that if we were to align this again, we're using project, then what will happen is that we'll get another curve on surface. So if I now go and have a look at those curves on surface, you can see we've got two of them, not just one. So if you need to align this surface back into the center of the other surface, one option is to delete the curves on surface and do a new project. So that will create us a new curve on surface. Or the other possibility is to use edge. Because we've created that curve on surface from the edge of our existing surface, then there's a good chance that this might give us a good result. Obviously in this case we wouldn't expect it to not be position aligned, as we've just done that operation. So you will often find that project is a better option when you're aligning into the center of a surface or you're trying to align to an existing trimmed edge. If edge doesn't work, then project is often the better choice. One thing to watch out for is if we're trying to project a surface onto another surface and there's a slight overlap in the edges, then when we try and use align, we may get an error message. So in the prompt it says align failed with error 3, projection failure. And what this means is that this edge is actually overlapping the edges of the other surface. So we can either extend this back a bit, or we can use shrink to fit, which will then give us a result. So this is the final case that we're going to look at in terms of G0 continuity. It looks very similar to the ones we've seen before. So let's try and align this. So we're going to go for G0 edge. We want explicit control on position influence of 1. And we're going to align the right hand surface to the left hand surface. And we'll increase the degree to 5 as we did before. And we don't get a good result at all. So what's the problem here? Well, the problem is to do with this surface, which looks like a Bezier surface, but in fact it's a NURBS. So let's just undo that, and we'll go and inspect this surface. So you can see that it's got degree 3, and it's got 3 spans, and if we put the isopalms on, you can see the knot lines. And the problem that we're getting is not to do with the fact that this is a NURBS, but it's a particular type of NURBS. It's actually been created from curves which have a chordal knot vector. One way to find out the details of the knot vector is to create a curve on this edge using duplicate, and we want no rebuild. So we now have a curve on that edge, and we want to inspect the edit points. So let's switch the edit points on here. And we'll go and pick nothing and pick all of those edit points. Now if we look at the information window, this will tell us where those edit points are being taken in terms of the parameter value. So Alias doesn't put these in the same order as you might expect, so we have to go and find the parameter values. They start at 0, that one, and end at 1. And the two values in between, 0.32 something and 0.64 something, show that we have a chordal knot vector. The best way to explain that, I think, is to show you some curves created with uniform knot vectors and with chordal knot vectors and show you what the difference is. So let's create a couple of curves, and we're going to start off with uniform knot spacing, degree 2, and we'll create a multi-span curve. And then we'll do the same thing again, but this time we'll use chordal. Now if we take those two curves and look at the edit points, and we'll inspect the edit points of the top one first of all. So you can see the parameter values start at 0, and they end at 4. And they're very regular. It's 1, 2, 3, 4. So that's what's called a uniform knot vector. Let's have a look at the one below. So again, it starts at 0, but then we have some odd values: 35, 70, 99 and 123. So those knot values are based on the actual arc length along this curve. Now when we're building surfaces, we should always use uniform. There's really no reason to use Chordal. And if we use uniform everywhere, then we won't get that problem with the align that we've just seen. So going back to this example, we discovered that this surface here has a chordal knot vector. And in fact we need a uniform knot vector if we're going to align this successfully. If we're stuck with this surface, we can always use Surface Edit, Rebuild Surface, go for a uniform rebuild with an appropriate number of spans and degree. So what we're going to do here is change the number of spans to the same values as we had before. So 1 by 3, and degree is going to be 3 by 3. And you can see this is only an approximation of the original. It says there's a maximum deviation of 0.46. We might choose to increase the degree to get it more accurate, but let's go with this. Now we're going to align the right hand surface again. So we want G0, edge, explicit control. Now we can't have degree 5 like we did before. We need degree 3. And we also need 3 spans. And with position influence of 1, we've got a perfect alignment in terms of G0. Hopefully you'll never have that problem. If you've created the surfaces yourself and you've always used uniform knot vectors, you're not going to have that problem. But sometimes you may have inherited a surface from somewhere else, and then you have to solve the issue. Now let's take a look at G1 continuity. So we've got a couple of cases here. We take the top one first. So we want G1. We're going to be aligning to an edge, and as before, for position continuity we want explicit control and position influence of 1 on. So we have absolutely no problem in achieving tangency in this case. We go to the lower one where we've got a tapered surface. Let's try the same again, and we find that we get a slight angle mismatch. Now the reason for this is because of the taper. Mathematically, Bezier and NURB surfaces don't like a difference in the taper of the second hull. So in other words, this one on that side and this one on this side. So the taper ratio between these two CVs here to these CVs here is quite different at this top end to the start end here. If we want to make the taper ratios exactly the same, we can switch on tangent balance, and that will show us a perfect result. But of course in this case that's not of much use. Alternatively, what we can try is reducing the amount of taper slightly. So as we reduce the amount of taper, we get closer and closer to the angle tolerance that we want. Here we've got an example where we're getting a tangency issue because of the difference in taper on either side of the edge. So on this end we've got quite a different ratio to the ratio on the other end. Now if we go into Align, and we try and align that right hand surface to the left hand one, we can't improve that. If we put tangent balance on, of course we get this result, which is perfect in one way, but of course the CVs are not in the right place at all. So the options here is we can either move this hull and see if we can improve it. So we've got tangency here now, but this edge is not the right shape. The other option is if we've got history on, we can go and extend this surface here using a tapered extend. Just drag it back a bit. So what we're doing is changing that ratio, and now we've got a tangency condition with a nice edge here. Obviously we could do some more adjustment on there if you wanted to change the shape of this slightly. When we come on to G2 continuity, we can use the same principle again. So on this end we've got a curvature problem, and on this end. And again it's down to the taper ratio being different at this end to this end. So we use a combination of adjustment in terms of extend, and see what that gives us. And by doing that, that's pulling these CVs in this direction. So we can then go into the history, pick up that align, And just move those CVs back a bit until hopefully we get curvature continuity. And it might involve pulling these points as well at the other end. And then we can do the same thing on this end. So we'll adjust the taper on that surface. And then look at the history of a line there. And see if we can get those CVs back into the right position so that we've got the right corner until we get a curvature alignment in that corner, hopefully. Again, these points might need adjusting as well. This method gives us a much cleaner result. The alternative is to just increase the degree, but for A-class work we always want to work as hard as possible to keep the surfaces as simple as possible. So here we have a simple example where we want to align this surface in G1 to this surface. Notice that these edges come off at a distinct angle, and we want to maintain that. And the other thing to notice is that in top view, this edge is a nice straight line. So again, we want to maintain that. So if we go in to try and align that, first of all, we could try skew, so that we keep those edges where they were. The only problem is this edge becomes curved, because these CVs are moving normal to the surface, so that's not really appropriate either. So we go for the vector option with Z, so these CVs can only now move in the Z direction, and we maintain that straight line. Now if we rotate that model around, you can see that CV pattern looks a bit jagged, and if we go into proxy display, that will show us the original CVs. So it's not giving us a great CV pattern there. So in some cases you might find that you can't achieve the tangency. In other cases you may find that the CV pattern is very distorted, and this is because of these edges coming off at an angle. So in general we want to avoid edges like that, and it's always better to have edge align if we can, but if it's not possible then we may have to resort to manually moving CVs around to try and get a nice pattern of CVs while keeping the tangency. In general, flowing edges, such as here where we've got edge align, always work better in terms of a line, in terms of the CV patterns, and in terms of the simplicity of the surfaces than having edges which come off at an angle. The other thing that helps is having the angles of the corners as close to 90 degrees as possible. We always want to avoid very acute angles. They make alignment more difficult, they make the CV patterns more difficult. We're now going to start looking at G2 and G3 continuity. So first of all we'll look at G2. So G2 alignment is going to affect the first 3 hulls, and we can move those hulls around much like we did with G1, either from the end or from the middle. If we go to G3, that now affects the first 4 hulls. And we've got edge align on here by default, so our edges here are flowing. Let's look at a real world example. So here we're trying to achieve curvature continuity on all of the edges, but you can see there's a couple of edges there where we haven't managed to do that. Now it may be possible with some more work to achieve that, maybe splitting up these surfaces into 3 rather than 2, maybe increasing the degree or the number of spans, but they're not very desirable results. With A-class work, as I've said before, we always want simplicity. So ideally, we'd want a surface in that corner which is degree 5 by 5 rather than having 2 higher degree surfaces. So the question is, why is curvature here a problem? And the reason is to do with this corner. So as we've seen before, when we have edges that flow, like we do across this way, then we don't get a problem. But where we've got an edge which is coming up here and then off at a different angle, then that can often cause alignment issues and also problems with the CV patterns. The other factor is trying to achieve corners which are as close to 90 degrees as possible. So for example, this corner is roughly 90 degrees, so there's no problem in alignment in this area. This one's okay. This angle here is greater than 90 degrees, but it's still close enough that that shouldn't give us an issue. So the main issue is just this edge not flowing into this one. If we make these edges flow, then you can see that we get a much better result. We've got a low degree going around here, and we've got curvature alignment on every single edge. Now in this area we've got a trimmed surface, so if we look at the CVs on that, you can see it's a trimmed surface, and in order to get this corner surface to align to it, what we've done here is we've used the trim convert construction method to create that. In other words, we've created a trim converted approximation of the trimmed surface with its edge here, and we've then used that to align this corner surface too in order to get curvature in all directions. Finally, we've deleted the trim converted surface. In the previous example, we saw how the result was improved by making the edges flow, but in this case we've got a very sharp edge here, and if we try and make that flow, then we'll end up with a worse result. You can see how much this struggles to get an alignment and how high the degree has to be and the number of surfaces, and it's all because we're trying to flow this edge into here. If this edge was coming off closer to 90 degrees, then flowing that edge would be a better result. So it's important to decide which way to go. If you've exhausted all the methods that we've talked about so far and you're still not achieving alignment, then there are some other things that we can do. If you're running surfaces over some main blocks, then make those G3 continuous rather than G2. The higher the level of continuity on the main blocks, the easier it is to achieve a high level of continuity on the secondary surfaces. Another possibility is to split surfaces around a problem area, or, as we've seen before, increasing degrees and span may be a solution. With A-class surfacing, of course, we want to always minimize the number of surfaces and the degree and the spans as much as we possibly can. It's also worth considering whether you actually need G2 on every single edge. If you've got very small geometry and you can achieve G2 everywhere apart from one edge where you're only getting G1, then that might be perfectly acceptable. The way to assess it is to look at the curvatures and the highlights and see whether you can see the problem in those. The final option is manual adjustment of CVs. If you've tried your very best to align every edge, then sometimes you'll find that only a few CVs need to be adjusted in order to achieve that final alignment without having to increase degrees, spans, or split surfaces up. Now this is an example where we haven't been able to achieve curvature at this edge, but we've got curvature on all of the other edges. What's worth trying is seeing if we get this to G3 continuity, whether that helps. So let's have a look at those surfaces. So we can see the curvature comes along, it's G2 continuous, but then it comes off at a different angle, showing that we haven't got G3 continuity. Now let's apply G3. So we've now got this nice flowing curvature here. And if we take those curvatures off, you can now see that we've got curvature there. It's not always going to be automatic that that's going to happen. In this case, we've got history on these edges. Unfortunately, it's resulted in curvature on that edge. If we just undo that for a minute so that we can see that clearly. So there's G2, and we're not achieving G2 on that edge, but the minute we put G3 in, we do. Sometimes company standards insist that for very small fillets, we use circular fillets. This means that they're going to be only G1 continuous everywhere. And they tend to be more difficult to align, especially where you've got a situation like this, where we've got one fillet overlapping another fillet. And you can see that we've got a large angle there, 4.67 degrees. Because the angle between these edges is very acute, it may not be appropriate to flow that edge through. And the same on this end, that we may not be able to flow that edge through. So often the solution is to split the surfaces instead. For example, like here, where we've had to split these surfaces to form very thin surfaces at the ends. Now this may not be ideal, but because the fillets are very small, then it really doesn't matter. It's more important to get everything to align than to worry about the highlights on a fillet that may be 0.5 millimeters in radius. In some of the previous examples, we've seen how in Align we can use vector with project to keep control of the CVs. So in this instance, we're looking down the Z-axis. So we've got project and Z on, and therefore the CVs will stay in the same position in this view. So it's a great way of keeping a nice pattern of CVs at all times. Now we can also use a vector with edge. So we put on Z again. And that will have the same effect of keeping these CVs looking all neat and tidy in that particular view. So we're looking down the Z-axis at the minute. In a case like this, where we've got a fillet which needs to align to this surface and to this surface, we find it's impossible to set up one vector for all of those CVs. What's useful here is to be able to use planes. So if we create a plane with geometry on this edge, we'll find that the normal of that plane is actually pointing in the direction in which we want to constrain the CV movements on this particular edge for the first 3 holes. Now we can also set up a plane on this edge. We don't need to go into those construction planes, but what we do need to do is get rid of the history on the planes. Now when we go into a line, so we want G2 on here with project on, and we're going to use picked as the vector option. So we pick the edge, we pick the surface that we want to align to, and then we pick the plane. And you can see there's a vector there, which is the direction in which those CVs will move. So we do the same thing on this edge. We'll pick the edge, we'll pick the surface that we want to align to, and then we pick the plane that we want to use. So there's our vector. And if you use those planes every time that you do an align operation on these edges, then your CVs are much more likely to stay nice and tidy. This is an example where we can't just use one vector to align this edge. If we rotate that, you can see it wraps around quite a lot. So the most appropriate setting here is if we go into a line with edge on, we'll use vector but normal, and that will mean that these CVs will move normal to this main surface. Now we've got position influence of 0 on, so let's try changing that to 1, see if we get a result, which in this case we do. Supposing we have quite a big gap between these two surfaces and we want to align this one to this one. So we're going to align it G2 edge explicit control position influence of 1, and we get that. Now the problem with that is it's introduced a bit of a blip into that surface. Suddenly we've gone from here to these CVs back here. So to soften that effect, we can use blending. Now blending works in combination with extra CV rows. So it's affecting that row, that one, that one, that one, that one, 5 rows in this case. And obviously we can change that. And then there's also a blend factor. The first thing that we notice here is that we've broken the continuity at this end. So we need to ignore these first 3 hulls. So we'll take the extra CV rows back a bit. So now we've got our curvature continuity back. But the blend doesn't look very good. Again, there's a bit of a disjoint between that end and this end. And that's where the blend factor comes in. But if we're trying to use blend and keeping continuity at one end, then we need to change the blend factor value, usually to 1. And that will give us a more progressive blend from one end to the other. Another use for a line with blend is if we've got a surface like this, and we've changed the main block surface so it's substantially different, we might want to move that shape onto this surface. So if we go into a line, and we're going to put blending on, but at the moment you'll notice it says extra CV row 0, and then we're going to align this edge to this curve on surface. So all that's done is pulled these CVs down so that we've got curvature continuity on this edge. But really we want to maintain the original shape as much as possible. So we can do that using blend. We've seen before that if we add extra CV rows, then we get a blended solution where we're keeping G0 on this edge. But if we want to move this edge as well, we can put 3 rows in there. So it's now pulling that edge down. But because we've got a blend factor of 1, it's sort of stretched this shape quite a bit. If we put the blend factor down to 0, then we get much more of the effect of moving that surface onto this new main block rather than blending it. And this is an incredibly useful technique. To save having to rebuild surfaces, we can actually reuse an existing surface and then move it into a new position.